How does one idea let a machine read a protein, a cell, and a paragraph, all with the same architecture? One idea. Let's find it. Picture a round conference table. 8 people, 8 tokens in a sentence. No one is at the head. Every person can look directly at every other person. That's the whole picture we're building. Before transformers, networks processed sequences like a phone chain. Word 1 whispers to word 2. Word 2 whispers to word 3. By word 100, word 1 is a rumor of a rumor. Long-range meaning is lost in translation. The transformer breaks the chain. Every token talks directly to every other token in one step. No hops. No decay. The line becomes a circle. Everyone hears everyone. But everyone hearing everyone isn't useful if everyone counts the same. Self-attention fixes this. Each token decides how much weight to give each other token. Thick line, strong connection. Thin line, weak one. Relevance is a number, and the model learns it. So how is that number computed? Every token plays 3 roles at once. A query, what am I looking for? A key, what I offer. A value, the information I carry. 3 vectors. 3 different questions. The match between a query and a key is a dot product. High dot product means what I am looking for lines up with what you offer. Low means we are pointing in different directions. That single number is the raw attention score. Raw scores don't sum to anything. Softmax does the conversion. Large scores become large weights. Small scores become nearly 0. The whole row sums to 1. Now we have a proper vote, a probability distribution over who to listen to. Take each value, multiply by its attention weight, add them up. That's the output for this token. It's a blend of everyone at the table, tilted toward the ones that mattered most. 1 token in, 1 richer token out. There's a catch. High-dimensional dot products produce huge numbers. Huge numbers crash Softmax into a single spike, and gradients vanish. The fix is 1 symbol. Divide every score by the square root of the key dimension. Softmax stays smooth. Training stays stable. One attention mechanism captures one kind of relationship. Syntax. Position. Topic. But language has many patterns at once. So we run several attention heads in parallel, each with its own Q, K, and V projections. Different heads. Different stories. Every head produces its own output vector. We concatenate them side by side, then apply one more linear layer. The result is a single token representation that carries every head's perspective. Many conversations. One summary. So here's part 1. Tokens sit at a round table. Each token sends a query, receives keys, and pulls a weighted mixture of values. We scale for stability. We run many heads in parallel. That is self-attention, end-to-end. Attention is the heart of the transformer. But a heart alone isn't a body. To actually train a model, we need the surrounding organs, position, processing, normalization, depth. That's what part 2 is. Here's a problem. Attention doesn't care about order. Shuffle the seats at the table, and the math gives the exact same answer. For language, that's a disaster. Dog bites man is not the same sentence as man bites dog. The fix is a simple one. We add a positional encoding to every token, a unique pattern of sines and cosines at different frequencies. Each seat gets a signature. Attention can now see not just who you are, but where you sit. After the table talks, each token goes home and thinks. That's the feed-forward network, a small two-layer MLP applied to every token independently. Attention was communication. The MLP is private computation. Deep networks forget their input. The fix is a residual connection. Whatever a block produces, we add the input right back in. If the block learns nothing, the input passes through unchanged. This is the gradient highway that makes depth possible. Every token's vector can drift, scale too big, scale too small. Layer norm rescales each token back to a clean baseline before the next block. It's not glamorous, but without it, deep transformers don't train. The encoder is the bidirectional reader. Every token sees every other token, past and future. This is how BERT reads a sentence. It is also how ESM reads a protein. The whole sequence, in one look. The decoder is a writer. It generates one token at a time, and it can only see tokens already produced, never the future. That causal mask is why GPT writes one word after another. It's also how scGPT predicts one gene after the next. Some tasks require both. The encoder reads the input. The decoder writes the output. A third connection, cross-attention, lets the writer peek at the reader's full memory. T5 works this way. So does AlphaFold. Now swap the tokens. Give the model amino acids instead of English words. Train on 250 million protein sequences. You get ESM, a protein language model whose attention patterns rediscover which residues touch each other in 3D. Swap the tokens again. Now each token is a gene, ranked by how expressed it is in one cell. Train on tens of millions of cells. You get scGPT, a foundation model that learns the grammar of cell states. Geneformer takes the same idea and sharpens it. For each cell, sort the genes by expression. Feed the ranked list as tokens. Attention learns which genes rise and fall together, and the model can rank therapeutic targets. And then there is AlphaFold. Its attention matrices are not just scores, they are distances and angles. The same mechanism that routes meaning in a sentence routes contact in 3D space. Attention learns to fold. One attention block is powerful. A stack of 12 is transformative. Each layer refines the representation the previous layer produced. By the top of the stack, each token carries the whole context compressed into a single vector. Depth is where the magic compounds. So what's the one idea? Let every token attend to every other, directly, in parallel, weighted by learned relevance. That's it. Swap the tokens and the same architecture reads English, proteins, and cells. One table. One mechanism. A different world.